Buffer solutions. Once look at this. Take pure water. Add few drops of HCl to it. Before that, pH of water is 7. Okay. After adding few drops of HCl, what happens to its pH value? Decreases or increases? pH value decreases because you are adding acid, so it will acquire acidic nature. Acidic solution is formed, so pH will be less than 7. When you add few drops of HCl, after adding HCl, pH will become less than 7. Similarly, for water, if you add few drops of base, few drops of NaOH, it will become basic. So pH is greater than 7. Clear? Right. But some type of solutions are there. Even though after addition of few drops of HCl or acid, few drops of base, their pH do not change. Particular solutions are there. Okay. After addition of acid or base, their pH do not changes. That solutions are called as buffer solutions. Right? The solution whose pH do not change upon addition of few drops of acid or base is called as buffer solution. Clear? Look at this. The solution whose pH do not change, whose pH do not change upon addition of few drops of acid or base. The solution whose pH do not change upon addition of few drops of acid or base is called as buffer solution. Right? Buffer solution is classified into mainly two types: simple buffer solution, and mixed buffer solution. Simple buffer and mixed buffer. Simple buffer is, what is simple buffer? See, simple buffer nothing but a salt of weak acid plus weak base. You know already. What is the example for salt of weak acid and weak base? Yesterday given salt of weak acid and weak base. Ammonium acetate, CH3COO NH4, ammonium acetate. So salt of weak acid and weak base. Identifying buffer is very, very important. Questions came previously on the examples only. Okay. You have to learn the combinations. Right. You will get question which of the following is the acidic buffer, which of the following is a basic buffer. Like that. Okay. Mixed buffer. Mixed buffer is classified into again two categories: acidic buffer, and basic buffer. Acidic buffer, basic buffer. Right? Acidic buffer. How to remember the examples? See, I'll give you one format. Acidic buffer is weak acid plus this weak acid salt with a strong base. Weak acid plus it's a salt with a strong base. Whenever you observe this combination, then only you have to consider that as a acidic buffer. I'll give you the combinations. Examples are very, very important. Okay, these combinations are most important. You know already the table, weak acids table, strong acids table. Say one weak acid, acetic acid, CH3COOH. Weak acid plus. Say it's a salt with strong base. This is weak acid, na? Take this weak acid and form a salt with strong base. CH3COONE. These examples are very important. Weak acid plus it's salt with a strong base. See, CH3COONE is the salt of weak acid plus strong base only, na? So weak acid and salt of strong base. Examples are very important. Can you frame another example? Can you say another example? Like take any other weak. Okay, HCN, NaCl. Examples are very important. Which of the following is acidic buffer? Which of the following is basic buffer? Third one, say another weak acid, H3PO4, weak acid, Na3PO4, HNO2, nitrous acid, not nitric acid, nitrous acid, and it's a salt. Okay, note like that. If you remember the format, then you can frame any number of examples. Weak acid plus it's a salt of strong base. So in acidic buffer, what are the components? In acidic buffer, what are the components? When we call a particular mixture as acidic buffer, if that mixture contains weak acid and it's a salt of strong base, then only we can call it as a acidic buffer. Got it? Online students, are you following? Sweta, how are you? Sweta. Meenakshi, are you following? Akshara, follow tunama? Ritika? Right. నిన్న కాన్సెప్ట్ చదువుకున్నాం అక్షర, ఫార్ములాస్ అన్నీ చదివావా? న్యూమరికల్స్ చేస్తాం మనము, చదివావా కాన్సెప్ట్ అంతా? Yes, tell me. After class I will send. Basic buffer. Can you guess the combination of basic buffer? Weak base plus it's a salt of strong acid. In the last class I given weak acid, strong acid, weak base, strong base. Okay, I'll send the video. Sweta, నువ్వు నిన్న జాయిన్ అవ్వలేదు కదా, ఒకసారి నిన్న క్లాస్ వీడియో పంపిస్తాను చూడు, ఓకేనా? Say one weak base, NH4OH, weak base, and it's a salt. You are taking weak base, na? So frame it's a salt. NH4Cl. NH4Cl is a salt of weak base and strong acid, right? So first you have to take weak base and you have to form one salt of that weak base with a strong acid. One another example, NH4OH and can I take like this ammonium sulfate? Can I take ammonium sulfate? Yes. Sulfuric acid, strong acid. It is salt of weak base and strong acid, like that. Zinc hydroxide, zinc is weak base, and ZnCl2. All these combinations comes under basic buffer. Let us do one numerical, very important model, right? Based on the limiting reagent, I'll give you. So we completed buffers. Buffer is the solution whose pH do not change upon addition of strong acid or strong base. Few drops only, few drops. That is the condition, right? Based on this idea, let us do one important numerical. Okay, right? So now you tell me, when we call particular mixture as a acidic buffer, when that mixture contains weak acid and salt of strong base, these two should be present. If weak acid is present and salt of strong base is present, then only we call it as a acidic buffer. Similarly, when we call particular mixture as a basic buffer, in that mixture weak base should be present and its salt with strong acid should be present. Okay, I'll give you one basic level question. After that, some moderate level question. Note that because numericals are important, so better to do few questions. Which of the following is acidic buffer? See, first combination, 0.1 molar 10 ml HCl plus 0.1 molar 10 ml CH3COONA. Second option, 0.1 molar 10 ml acetic acid plus 0.1 molar 10 ml NaOH. 0.1 molar 10 ml acetic acid plus 0.1 molar 10 ml. Very easy question. Third one on the basic level question. See, in this mixture weak acid is present and its salt of strong base is present. Clear? First one is not correct. Why? Strong acid. According to definition, what is acidic buffer? Weak acid should be present. So this is wrong. Here base is present, not salt. Okay. Very simple question, basic level question, but you should learn other combinations also. Acetic acid is easy, you can identify, but when you get other acids, you have to identify, like phosphoric acid, HCl, carbonic acid, right? Let's go through the table. Next level questions, some moderate level questions. You observe carefully, we apply limiting reagent in this. Stoichiometry related. Which of the following combination form acidic buffer? Which of the following combination form acidic buffer? First combination, 0.1 molar 10 ml acetic acid plus 0.1 molar 10 ml NaOH. Second option, 0.1 molar 20 ml acetic acid plus 0.1 molar 10 ml NaOH. I am giving two combinations to you. Which combination form acidic buffer? Okay, look at this. How to approach this question? First of all, write the equation between acetic acid and NaOH. Equation between acetic acid and NaOH. See, acetic acid plus NaOH gives CH3COONA. Salt, When we mix acid and base, we'll get salt and water, right? Once observe the mole-mole relation. Buffer question related to stoichiometry. Clear? Mole-mole relation. Is this equation balanced or not? Once check. This is a balanced equation. This is a balanced equation. So you no need to balance. First check whether the equation is balanced or not. Now what is the mole-mole relation? Acetic acid is 1 mole. Sodium hydroxide is 1 mole. This is 1 mole or 1 mole, 1 mole, 1 mole, right? The reason is there. Why I am writing the mole relation. Okay, right. Now, according to the given data, write the moles of acetic acid. Now, this is according to standard equation 1, 1, 1, 1, right? But according to the data, how many moles are given to you? How to find the moles? See, this is general equation. Now coming to the question, first one. How many moles of acetic acid is present? What is the formula for number of moles? Number of moles is equal to molarity into volume. Number of moles is equal to molarity into volume. Molarity is 0.1, right? And volume is 10 ml. How many moles? 1 mole. Mole of, we are checking first combination. Clear? So in the first option, moles of acetic acid are 1 and moles of sodium hydroxide. How many moles? Same formula. Number of moles is equal to molarity into volume. Molarity is 0.1 and 10. Here also 1. Right? Now let us write the equation again. This is general equation. Now acetic acid is 1 mole according to the given data. This is 1 mole. This is also 1 mole to give 1 mole of sodium acetate and 1 mole of water. Now once you go back to the definition of acidic buffer, what is acidic buffer? When we call particular mixture as acidic buffer, for example, see in a beaker, acidic buffer is present. This is acidic buffer. Means inside what is present? This beaker name is acidic buffer. Inside acidic buffer is present. Means inside what may be present? Weak acid should be present plus it's a salt of strong base. It's a salt with a strong base. If these two are present, then the total beaker is called as acidic buffer. Inside beaker, if weak acid is present and salt of strong base is present, then you can call total beaker as acidic buffer. But look at this. According to the given data, 0.1 mole of acetic acid is 1 mole of acetic acid is reacting with 1 mole of sodium hydroxide. Is there any weak acid remaining? 1 is consumed by 1. Clear? 1 mole, both are consuming to form sodium acetate. Is there any weak acid in the beaker? In this beaker, observe. What is said that when we call particular beaker or mixture as a acidic buffer, it should contain weak acid. It should contain salt of weak base, strong base. But in this beaker, you tell me, is there any weak acid? No. Only salt and water is present. So first combination do not form acidic buffer. Because 1 mole, both are consumed to form salt. Where is weak acid? Weak acid is not present. After reaction, is there any weak acid? But according to definition of acidic buffer, weak acid should be present. Clear? Got it, online students? Why first combination is not forming acidic buffer? Because 1 mole is consumed by 1 mole to form 1 mole of salt and 1 mole of water. Weak acid is not remaining. Got it? Follow అవుతున్నారా అక్షర? అర్థమైందా లేదా? రీతిక ఉన్నారమ్మా మీరు? శ్వేత ఏంది ఎవరు మాట్లాడట్లేదు? Now check second combination. What is second one? 0.1 molar 20 ml acetic acid, 0.1 molar 10 ml NaOH. Let us check for that. What is second combination? 0.1 molar 20 ml acetic acid. Find out its moles. 0.1 molar 10 ml NaOH. Find the moles. What is the formula of moles? Number of moles is equal to molarity into volume. Molarity 0.1 into volume is 20. And here also later on, that's why. Here 2 moles. Molarity into volume 0.1 into 10, that is equal to 1. Now moles of acetic acid is 2, moles of sodium hydroxide is 1. To write the equation, CH3COOH plus NaOH gives rise to CH3COONA plus H2O. Right. Now apply the limiting reagent. Limiting reagent. What are the moles according to the data? 2 moles. Here what is the moles according to the data? 1 mole. 2 mole and 1 mole. Right. Now what is limiting reagent here? What is the limiting reagent? Sodium hydroxide or acetic acid? How to get limiting reagent? See, how to get limiting reagent? A mole divided by coefficient. 2 moles. What is its coefficient? 1. 2 by 1. Mole divided by coefficient. Here 1. 1 by 1. 1. So which is least value? NaOH is the least value. So this is limiting reagent. This is limiting reagent. NaOH is a limiting reagent. LR, limiting reagent. According to limiting reagent, we write the moles of product. I explained in the stoichiometry also. So, according to moles of NaOH, CH3COONA is formed. Now, according to standard equation, 1 mole is giving 1 mole. 1 mole is giving 1 mole. And according to the data also, moles are 1 only. According to the given data, see, here coincidentally both are same. Okay. 1 here also 1. Okay. Right. 1 mole of sodium acetate is formed. Okay. Now coming to the acetic acid moles. After reaction, how many moles of acetic acid will remain after reaction? See, which is a limiting reagent? NaOH. Which is excess reagent? Acetic acid. Excess means after reaction acetic acid will present. Very simple thing. You no need to do any further simplifications. Very simple thing. What is limiting reagent? NaOH. NaOH is limiting reagent means sodium hydroxide. So acetic acid is excess. So after reaction also it will present. See, in the final mixture, see, this is the beaker, final beaker. In the final beaker, sodium acetate is present and acetic acid also present. What I explained, excess reagent. Excess means after reaction also it will present in the final product. What is acidic buffer definition? Weak acid plus its salt of strong base. Forming or not? So second combination will give acidic buffer. Very, very important model question. Got it? NaOH is the limiting reagent. Acetic acid is the excess reagent. Excess means after reaction also it will present. Clear? Right. This is one important model question on the buffers. Next, pH of acidic buffer. Keep heading. pH of acidic buffer. How to calculate pH of acidic buffer? This are at pH of basic buffer. pH is equal to pKa plus log salt concentration by acid concentration, or pH is equal to pKa plus log normality into volume of salt divided by normality into volume of acid, or another formula pH is equal to pKa plus log, see, number of moles into n factor of salt divided by number of moles into n factor of acid. This is also very important. Okay, just remember the formulas. pH is equal to pKa plus log salt by acid, n into V of salt by n into V of acid. N factor, where n is equal to, this n is equal to number of moles. This is n factor. N factor nothing but in case of salt take the charge. In case of acid take a basicity. N factor for acids is basicity. H2SO4 n factor is 2. Why its basicity is 2? It gives 2H plus ions. For salt take the charge. Right. Coming to the basic buffer. POH is equal to pKb plus log salt by base. But what is our heading? pH. But in the formula what is there? POH. After getting POH we will do 14 minus POH. By using that relation you can find. First you will get POH when we use this formula. Then pH is equal to 14 minus POH. And remaining formulas are same. N into V of salt by N into V of base. N into N factor of salt by N into N factor of base. Same as it is. Copy paste. Copy paste. Clear. Online students. Got it? ఫాలో అవుతున్నారా మీరు? Yes, tell me. Okay. Completed. Right. Next. Buffer capacity. Buffer capacity. Buffer capacity. How to define buffer capacity? See, according to definition, what is buffer solution? What is a buffer? The solution which resists the change in pH upon addition of few drops of acid. Few drops of acid are base. Few drops of acid are base. But if you add more amount of acid or base, for example, some 1 liter, then it will change. So definition is applicable, or in definition we mentioned few drops of acid or base only, but if you add more amount, then it will, pH will change. Clear? So buffer capacity is the number of moles of strong acid or strong base added to 1 liter buffer solution to change its pH by 1 unit. 1 unit. Number of moles of strong acid or strong base added to 1 liter buffer solution to change its pH by 1 unit. The number of moles of strong acid or strong base added to 1 liter buffer 1 liter buffer solution. To change its pH, by 1 unit. To change its pH by 1 unit. Right, see the formula. Number of moles of acid or base, number of moles of acid or base divided by delta pH. Delta pH stands for change in the pH. Okay, right. Next, solubility. Solubility S. Solubility symbol is S. See the number of moles of sparingly soluble salt. Sparingly soluble means slightly soluble. Sparingly soluble salt. Sparingly soluble salt. The number of moles of sparingly soluble salt present in 1 liter solution is called as right. See, the number of moles of sparingly soluble salt present in 1 liter solution is called as a solubility SI. Okay. See, solubility always expressed in mole by liter, not molarity. Very, very important. Solubility always expressed in mole by liter because number of moles present in 1 liter solution. Very, very important. Solubility is expressed in mole per liter. Solubility symbol is S. Next, solubility product. Solubility product KSP. How to define solubility product? Let us take a saturated solution. Saturated, unsaturated, supersaturated. We have different types of solutions, right? Let us take one saturated solution of salt A and B. Means A cation and B anion is present. Right. This is salt solution. Saturated salt solution. Saturated. Okay. Now solubility product KSP. It is the product of. It is the product of concentrations of cation and anion. Cation and anion in a saturated solution. Saturated solution is the condition. KSP is equal to what is cation? A plus anion is B minus. So KSP solubility product is the product of concentrations of cation and anion present in a saturated solution. Solubility product. Okay. Now let us see solubility product for different types of salts. KSP for AB type salt, for AB2 type salt, for AB3 type salt, and so on. AXBY type salt. First of all, let us see solubility product for AB type salt. Once look at this. What is the subscript of A? 1, B1. A1. B2, B3. First of all, see the subscripts, right? Solubility product KSP for AB type salts, 1 power 1, again 1 power 1, S power, add these two, 1 plus 1. 1 power 1, 1, 1 power 1, 1, S power 1 plus 1. So KSP is equal to S square. Solubility product is S square. Next, AB2 type salts. For AB2 type of salts. First of all, what is subscript 1? 1 power 1, 2 power 2, subscript power subscript only, right? S power 1 plus 2, S power 1 plus 2. So KSP for AB2 type of salts is 2 square is 4, 4 is cube, important for the numericals. Next, for AB3 type, KSP is equal to, say, how many students? 1 power 1, subscript power subscript, 3 power 3, but add powers, S power 1 plus 3. Then value is 27 S power 4. 27 S power 4. Now, what are the examples for AB type salts? AB type sparingly soluble salts. Examples AB type. AgCl. AgCl comes under which type? AB type only. Now what about this one? BaSO4. BaSO4 comes under which category? AB type category. Sparingly soluble salt. Right. AB2 type. CaF2. CaF2. AB2. Here one cation, one anion are there. That's why AB type. Here AB2. 2 fluoride ions. This one AlCl. AlCl3. You can apply this logic for any type of salt, right? Now you tell me A2B3. You tell me A2B3. Solubility product for A2B3 type. Tell me what is KSP value? Two power 2, 3 power 3. 108 S power 5. Okay, and S power 5. And generalization Ax by is equal to, for this write directly, KSP is equal to x power x, y power y, s power x plus y. This is generalization. Okay, for general salt, any type of salt. Let us do one question on this. Find the solubility of CaF2 whose KSP, on basic level question, whose KSP is 4 into 10 power minus 2. Find the solubility of CaF2, calcium fluoride, whose KSP, whose solubility product is 4 into 10 power minus 2. What is solubility product for this? This is in the form of AB2 type. For AB2 type, what is the solubility product? KSP is equal to 4s cube, right? Correct or not? AB2 type salt. KSP, how much given to us? KSP 4 into 10 power minus 2 is given. That is equal to 4s cube, right? 4 will get cancelled. So s cube is equal to 10 power minus 2 and s is equal to 10 power minus 2 by 3. This is random data given to you. Clear? Generally, you will get appropriate data, no need to vary. For example, if I take, instead of that, if I take -3, then that will be correct, right? Sufficient data, like this. So S is equal to 10 power 3, 3 will get cancelled, 10 power minus 1, that is equal to 0.1 mole per liter. You will get appropriate data only, no need to vary, okay? But see the procedure, how we did this. Right, okay, this is a basic level question. Now let us see very important. Solubility of sparingly soluble salt. This question came 3 times in the NEET. So let us do that question. Finding solubility of a sparingly soluble salt in the presence of strong electrolyte. Finding solubility of sparingly soluble salt means weak electrolyte in the presence of a strong electrolyte. See the procedure, keep heading. Solubility of sparingly soluble salt in the presence of strong electrolyte. Important model for NEET. Solubility of sparingly soluble salt. Sparingly soluble salt in presence of strong electrolyte. In the presence of strong electrolyte. First of all, you should understand the question and you have to identify which is a strong electrolyte, which is a weak electrolyte. Sparingly soluble salt means weak electrolyte whose dissociation is very less. Once look at this all. Before going to the question, I will explain one small topic to you. I am taking CH3COONA. General topic. This is a general topic. Or CH3COOH. Sorry. One general topic I am giving to you. This is HCl. Which is strong acid? HCl is the strong acid. Now dissociate these two in water. Dissociate in water. Now you tell me, from which acid more number of H plus ions will come? Obviously HCl only. HCl release more number of H plus ions because that is strong. Acetic acid gives very less number of H plus ions. For example, you are taking 100 here also we are taking 100. 100 HCl molecules will produce 100 H plus ions. 100 H plus ions. But acetic acid is a weak acid. It gives only some approximately some 2 H plus ions. Just generally I am giving. Observe 102, which can be neglected. Compared to 102 can be neglected or not. This idea is useful in this question, right? So we can neglect the ions which come from the weak electrolyte or weak acid. We can neglect the ions which come from weak acid or weak electrolyte or sparingly soluble salt. Sparingly soluble weak electrolyte all are same only. Clear? Remember this part. Okay, now I use this general concept in the question, this question. We can ignore the ions which come from the weak electrolyte or weak acid. Remember the point. First I will give the question. Based on that question, we will do. Right. Find the solubility of AgCl in the presence of 0.1 molar NaCl within the bracket Ksp of AgCl is equal to some 2 into 10 to the power -4. Very important model for the NEET. Okay, you are going to calculate the solubility of AgCl in the presence of 0.1 molar NaCl. Before that, I will give you one generalized explanation for you. Once look at this, all of you. Take plain water. Okay, without any solute in it. Okay. In the second case, take 0.1 molar NaCl. In the third case, take 0.2 molar. This is also important theoretical question. Now I am adding AgCl in 3 samples, dissolving AgCl in 3 samples. I am dissolving here, I am dissolving here, and I am dissolving here. My question is very simple. You can apply the logic here. Now you tell me in which beaker it is more soluble. Beaker 1, beaker 2, and beaker 3. In beaker 1, water is present. In beaker 2, 0.1 molar NaCl is present. In beaker 3, 0.2 molar NaCl is present. My question is, in which beaker AgCl is more soluble? In which beaker AgCl is more soluble? Very simple question. You can answer, you can guess. You are dissolving AgCl salt in 3 beakers. In which beaker it is more soluble? Third only. In first beaker it is more soluble. Why it is more soluble in first beaker? Because it is not having any chloride ions. Clear? It is a simple plain solution. More space is there for Ag plus and Cl minus ions. But here already chloride ions are present or not? Some space is occupied here. There is no space, no more space for the dissolution. Clear? And in third one, more amount of chloride ions are present. More amount of chloride ions are present. So if any common ion, see, if any common ion is present, common ion means here chloride is there, here also chloride is there, then solubility will be less. Already chloride ions are present. For example, take one empty bench. On empty bench, more number of students can sit or not? Huh? This is empty. Is there any chloride ion in it? No. So more number of AgCl particles will dissolve. If already few students are sitting on the bench, can new student will come easily? No. Already some chloride ions are present inside it. So new chloride ions will not come. Possibility is less. So in the presence of common ion, solubility is less. 0.2 molar means more chloride ions are there. So dissolution is less. Clear? This is also very, very important theoretical question. The solubility of AgCl is more in plain water compared to the solution with common ion. Got it, all of you, online students? Follow avutunnara meer online vallu? Okay. Right. Now see the question. We are going to calculate the solubility of AgCl in the presence of 0.1 molar NaCl. Of course, here solubility is lesser. So we are going to calculate the less solubility only. Solubility of AgCl in plain water, in 0.1 molar NaCl, in 0.2 molar NaCl, like that. In different cases, we are going to calculate the solubility. Now I choose this option. Solubility of AgCl in the presence of 0.1 molar NaCl. See the procedure. Clear? First of all, you have to identify the weak electrolyte and strong electrolyte in the given data. How to find weak electrolyte and strong electrolyte in the given data? Look at this, all of you. First of all, now you tell me what is the question? Find the solubility. Whose solubility you are going to calculate? AgCl. Whose solubility you are going to calculate? Consider that as a sparingly soluble salt or weak electrolyte. Whose solubility you are going to calculate? Consider that as a sparingly soluble salt or weak electrolyte. Got it? Find the solubility of AgCl. So AgCl is the sparingly soluble salt. In the presence of which salt you are going to calculate? In the presence of in the presence some salt will come, that will be the strong. Simple logic. So in the question, in the given data, you have to identify which is a sparingly soluble salt, which is a strong salt or strong electrolyte. This is very, very, very important. Identifying sparingly soluble salt and identifying strong electrolyte. Right. Now see the procedure. First, dissociate strong electrolyte. NaCl dissociates into Na plus and Cl negative. What is its concentration? 0.1 molar, 0.1 molar, this is also 0.1 molar, all are 0.1, 0.1, 0.1. Clear? Right. Next coming to the sparingly soluble salt, AgCl. See the procedure. First we wrote dissociation of strong electrolyte, after the dissociation of weak electrolyte. AgCl gives rise to Ag plus and Cl negative. Now consider solubility. We are going to find the solubility na? Solubility as S. Solubility as S. Now you tell me, Cl minus ions coming from weak electrolyte. Clear? Yes, sir. Plus Cl minus ions are coming. See this diagram. Where are they? I cleared that. Sorry. This diagram I given na. AgCl and 0.1 molar NaCl. See, Cl minus ions are coming from NaCl and Cl minus ions are coming from AgCl also. Already Cl minus ions are present in the beaker, and again Cl minus ions are coming, right? But you tell me this is weak electrolyte na, so we can ignore S, because S is the concentration of chloride ions due to AgCl. S is the concentration of chloride ions from AgCl. So can I take like this 0.1? Why I am ignoring S? Because S is the concentration of chloride ions coming from the weak. You can neglect acetic acid story explained na. HCl is giving 100, acetic acid is giving 2 only, so you can ignore 2. Clear? S is the concentration of chloride ions from AgCl. 0.1 is the concentration of chloride ions from NaCl. So you can ignore S. Okay, note down up to this. Right. Once again look at this. S is the concentration of Ag plus ions coming from AgCl. Here also S is the concentration of Cl minus ions coming from AgCl. Once you look at this diagram, in 0.1 molar NaCl, you are adding AgCl. Means in the beaker, you have chloride ions coming from the two sources. First source is from 0.1 molar NaCl. Already chloride ions are present and you are adding AgCl. But AgCl is a weak electrolyte, no? So Cl minus ions from the AgCl can be neglected. That's why S plus 0.1. 0.1 is the chloride ion from NaCl, more concentration. S is the concentration of chloride ions from AgCl. AgCl is sparingly soluble salt, weak electrolyte. So S can be neglected. S plus 0.1, 0.1. For example, see 1 plus 1 lakh or 10,000 or 1 lakh. Can we neglect this one? Because this is bigger value, you can neglect it. You can neglect it. Right? Now, S and 0.1. S and 0.1. What is solubility product of AgCl? What is solubility product of AgCl? Ksp is equal to Ag plus ion concentration into Cl minus ion concentration. Solubility of Ksp is equal to Ag plus ion concentration into Cl minus ion concentration. What is Ksp given to you in the question? 2.2 into 10 power minus 4, not 2.2 into 10 power minus 4. 2 into 10 power minus 4. Ag plus S value. Cl minus 0.1. Then S is equal to 2 into minus 3. Let us do another model question also. Wait, I'll explain until you will get. Same model, everything is same. First of all, procedure, write the equation for strong. Which is strong here? In the presence. NaNO3 dissociates into Na plus and NO3 minus. Its concentration 0.1, 0.1 and 0.1. After that, weak. What is weak? Whose solubility we are going to find? That is weak electrolyte. Okay, AgNO3 gives rise to Ag plus and NO3 minus. This is S. This is S. S plus 0.1 because nitrate ions are coming from both AgNO3 and from NaNO3. Nitrate ions are coming, but AgNO3 is a weak, so you can neglect S value because S is the concentration of NO3 minus ions from AgNO3. You can neglect it, so here you can consider 0.1 only. This is S. Now what is KSP of AgNO3? 2 into 10 power minus 3. Now write KSP is equal to Ag plus concentration into NO3 minus concentration. 2 into 10 power minus 3 is equal to Ag plus is S. See, Ag plus is S. And NO3 minus is 0.1. So S is equal to 2 into 10 power minus 2 mole per liter. Right, one more question on this. Find the solubility of AgF, not it. In the presence of 0.2 molar MgCl2. Within the bracket KSP of AgCl is equal to some 4 into 10 power minus 2. Here strong electrolyte is MgCl2. Before that I took NaCl only, like AB types also I took. Here AB2 type MgCl2. If 2 is there, then how to take? What is the procedure? First write dissociation of strong electrolyte. Which is strong electrolyte? In the presence of. So this is the strong. MgCl2 dissociates into Mg plus 2 plus 2Cl negative. What is MgCl2 concentration? 0.2. This is 0.2. Chloride ions concentration 2 into 0.2, that is equal to 0.4. That's why given. If coefficient is there, then we have to multiply. Now remaining procedure is as it is. AgCl gives rise to Ag plus and Cl negative. This is S, this is S. Chloride ions S plus 0.4, that is equal to 0.4. 0.4, this is S. Now this is Ag plus concentration, this is Cl minus concentration. Now KSP value is equal to Ag plus solubility product Cl negative. KSP how much given to us? 4 into 10 to the power of minus 2 is given to us. Ag plus is SC, yes. Cl minus is 0.4. And how much we will get? 10 power minus 1, that is equal to 0.1. Right. This is a very, very important mode. Next, keep heading ionic product. Ionic product. Ionic product. Ionic product. See, saturated, supersaturated and unsaturated. You have two types of solutions. Saturated solution, unsaturated solution, supersaturated solution, right? Solubility product is the definition applicable for saturated solution only. In solubility product definition, what we discussed, it is the product of concentration of cation and anion in a saturated solution. Clear? But ionic product KIP is applicable for any type of solution. It may be saturated or it may be unsaturated or supersaturated solution. This is also same. Ionic product KIP is the product of concentration of cation and anion in any solution. KSP is for only saturated solution. KIP is for any type of solution, saturated, unsaturated, supersaturated, any type of solution. Clear? Now, one important condition you have to write. Definition is clear for ionic product. Product of concentration of cation and anion in any type. One important condition for precipitation. What is the meaning of condition? See, when you add two different solutions, when precipitation formation takes place. When precipitation, this is also important model. You are adding two salt solutions, whether precipitation formation will take place or not. Clear? Right. Condition for precipitation. KIP, if ionic product is greater than solubility product, then precipitation takes place. Condition for precipitation. If ionic product is greater than KSP, then precipitation takes place. Then the formed solution is called supersaturated solution. If precipitation is formed, that is called as a supersaturated solution. Okay. This is theory part. I will do the numerical part tomorrow. Okay.